Hi everyone, welcome to my video report of Lab 3 in Physics 2 class at Georgia Tech. In this lab, we focus on the concepts of magnetic field, and we completed two major experiments in this lab. In the first experiment, we determined the distance dependence relationship with the magnetic field of a bar magnet. In the second experiment, we compute the magnetic field at an off-axis location using both the program and the real-time measurements. In this lab, we used the magnetometer app on the smartphone to measure the magnetic field at the desired location. Note that at the beginning of the lab, we need to align the smartphone in the magnetic north-south axis to compensate for the impact of Earth's magnetic field in our system. Also, using the magnetometer app and the bar magnet, we found the approximate location of the magnetic sensor on the smartphone so that we can make more accurate distance measurements in the following experiments. In short, with those preparation steps, we are able to assume the approximation that the change of X component of magnetic field in the following measurements is only caused by the magnetic field of the bar magnet. In the first experiment, we want to find the dependence relationship between the distance and the magnitude of magnetic field. Using the formula there, where K is a constant consisting of the mu, the magnetic dipole moment, as well as mu0/4pi, which is the magnetic constant. We measure the distance between the bar magnet and the sensor, given that the net magnitude of X component of magnetic field at the sensor is 20, 70, 120, 170, and 220. We observe that as the distance decreases, the magnitude of magnetic field increases. We also want to determine the exponential coefficient, which is n, in the equation at the top. We will use the logarithm version to compute this. Using the measured values in the previous table, we plot the graph on the right, which is log of X component of magnetic field versus log of distance r. Note that n is exactly the slope of the line of best fit in the graph, which is negative 2.8831. Note that log k is the intercept of the equation, and we can use the formula K equals mu0/4pi times 2 mu to derive the magnetic dipole moment, which is 3.3.651 in this case. In a second experiment, we compute the magnetic field of the bar magnet at an off-axis location. Down below is the link to my code implementation of the model. Feel free to have a look at it and follow along my explanation. To compute the magnetic field in the program, we use the formula on the screen. Note that now distance from bar magnet to the observation location, which is the sensor, has both non-zero X and Y components, and the actual magnetic field is the magenta arrow on the top right. These are the results. One retrieved from program computation when using the measured values. Note that the computed magnetic field is larger than the magnetic field using measured values. One possible reason is that as I move the smartphone along the axis, the magnetic field might be affected by the surroundings electronic devices, and the 0x component at the original location does not hold to be 0 at other locations. There are also some additional questions. What if we didn't orient the sensor to compensate for magnetic north? In this case, not only the bar magnet, but also the Earth will contribute to the X component of magnetic field at the place of measurement. Therefore, in the experiment, the magnetic field of bar magnet will be smaller than what we have expected, and the distance from the bar magnet will be larger than expected. This can lead to a smaller intercept of the fit line and eventually a smaller magnetic dipole moment. What if we stick two identical magnets together? We should expect to have a stronger magnetic field, because two identical magnets together can generate a larger magnetic dipole moment. To be more precise, the magnetic field should be exactly twice as large as a result of current experiment. Because in our applied formula, the magnitude of magnetic field has a linear relationship with the magnetic dipole moment, and the magnetic dipole moment should be twice as large as the one for a single bar magnet. This is the end of my video report. Thank you for watching.